Okay, so well, thank you everyone. And with that, we conclude this session on distributed security model, why that matters now. I'd like to thank the entire team, Floyd DaCosta, for being such a flawless moderator. Thank you. We had no intentions to scare you away, but definitely thank you once again for keeping to the time limit provided. And Dr. Pradeepti, Dr. Surya, and Professor Anvita. Um, um, Anvita Mandata for joining us for this particular session and sharing with us your views. Now we'll move on to our next session on cyber math and mathematics behind provenance, observability, and automated reasoning concepts of security. And as mentioned, we have another track session going on, a parallel session in the next auditorium, which is called a stage 1. And that's where you have to be if you want to attend a session on privacy, which is a new field throwing unprecedented, voluminous, complex, and intertwining problems. You may refer to the schedule on top. An icon right next to lobby is where you can find the entire program agenda and refer to it and make a choice for which session you'd like to attend. So that is the session on privacy, which is going on in stage 1. And in this, the main auditorium, we now have our next session on cyber math. And joining us for this session, we have Dr. Vireshwar Kumar, Assistant Professor in the Department of CSE at IIT Delhi. Dr. Anindita Banerjee, my apologies, Adjunct Scientist Corporate R&D, C-DAC, Pune, and Dr. Shweta Agarwal, Associate Professor, CSE at IIT Madras, joining us as panelists. And as a moderator, Professor Saumitra Sanadhya, Associate Professor at IIT Jodhpur, will be leading this session and moderating it for all of us. So I'd like to welcome all of our panelists and the session moderator. And without any further ado, hand it over to you, Professor Sanadhya, to take it forward from here. Thank you.
Yeah, thank you very much. Are all panelists on the stage? Because I'm not able to see them. I only see Dr. Vireshwar. Are other panelists also on the stage?
I can just see you, Professor Sabali.
Yeah, which is what? I am only able to see the two of us. So, yeah, okay. Now Dr. Shweta is also here. Great. And Dr. Anindita maybe? Okay. So maybe I begin after Dr. Banerjee joins, and after maybe Samriddhi introduces the all of us, or should I start? I don't know. I'm just waiting for Dr. Banerjee to join.
Hi, Professor Sanadhya, can I request you to now start the session? All of
Thank
our
you.
panelists have already joined. Yes. Thank
Okay,
you.
thank you very much. Thanks DSCI and Ministry of Electronics and Information Technology for giving us this opportunity to have a discussion on in this extremely important topic of cyber math behind provenance, observability, and automated reasonings, and how it relates to the security. So we have some wonderful colleagues with us to discuss this topic, and maybe I would like to start with the talking about the way confidentiality and provenance of messages is ensured by using mathematical techniques in the modern security industry is today. So Dr. Vireshwar Kumar from IIT Delhi's CS department, can I ask Dr. Vireshwar to maybe make a comment on this initial topic?
Yeah, sure. Thanks, Professor Saumitra. So, hello everyone. Yeah, thanks DSCI for inviting me. This is a very interesting topic because today in this session we will be talking about the fundamental mathematics on which the whole security architecture relies on. So, if I look at this security architecture, I consider it from a network security perspective, and therefore I see it at three levels. So the first level, the highest one, would be looking at the network security, and then the second level will be there. You are talking about security protocols, and at the base of all of these is the cryptographic primitives, which are actually utilized to develop the security protocols, and then the protocols are developed and elaborated further to ensure network security. So now looking at this, the basic aspect of cryptographic primitives. So then you know that we have two different types of cryptography. We have symmetric key cryptography and we have asymmetric key cryptography. So basically in the symmetric key cryptography, we typically depend on this idea of having some sort of permutation or some sort of substitution to make sure that the whatever security goals you have set are satisfied. Now, when we look into the asymmetric cryptography, then we have a variety of solutions which have very different flavors. So I think so of course symmetric cryptography has been there for a very long time. But the asymmetric key cryptography or public key cryptography came into being in 70s. So the first mathematical problem, or I would say mathematical tool that was being utilized there was that people started looking into modular exponentiation. So exponentiation over a modulus. And then, of course, multiple researchers came up with these different protocols or primitives which depended on some mathematical problems. So for instance, first of all, Diffie-Hellman key exchange protocol was developed, and that depended on the discrete logarithm problem. And around the same time or slightly later, RSA was proposed, and that problem was based on the problem of factoring large numbers. And with these two the tools in our hand, the Diffie-Hellman key exchange protocol and RSA, things progressed very well. And then at some point, this area of this whole new area of elliptic curve cryptography came up, where people now started depending on this algebraic structure of elliptic curves. And basically, the problem that people looked at was just looking into this elliptic, you can say elliptic curve discrete logarithm problem. So finding the discrete logarithm of a random elliptic curve element with respect to a known base point. So they figured that this is also a difficult problem to solve, and therefore the newest cryptographic protocols utilize these elliptic curve cryptographic tools. So yeah, with that brief description of this whole history of this development of these basic tools, I will send this stage to rest. So send my comments to rest, and then I will ask Professor Saumitra to take us forward.
Yeah. So thanks, Dr. Vireshwar, for this interesting discussion on the history of how the public key cryptography developed. And as we see this today, it is essentially related to a trapdoor one-way function. So if you have a trapdoor one-way function, we can prove that it is possible to have a public key cryptography. And the two great examples that you gave from history are related to the RSA problem and the discrete log problem. And we know that if we do have large-scale quantum computers at any point of time, then both these problems will be broken. And that will imply that our modern cryptographic infrastructure, which is being used in industry A's today, will be completely broken. So that brings me to our next panelist, Dr. Anindita Banerjee, who is not only an expert on quantum algorithms and quantum protocols, but is also involved in implementing these protocols to practice. So, Dr. Banerjee, welcome, and I would like to ask you the next question about can you talk about the security in the quantum world, and what kind of mathematical problems do we use to secure messages, or even to prove provenance of messages in this setting?
Thank you for this kind introduction. And I would again like to start by thanking DSEI for inviting me. So let me start answering this question with a famous quotation by Simon Singh. He said that, that Second World War was the physicist war because the atom bomb was detonated. And the Third World War would be mathematicians' war, because the mathematicians will have control over the next great weapon, which is information. So now coming back, and if you just look back, cryptography has been as ancient as civilization, and every time we thought that it is the best one, but with the emergence of new technology, it had to go through a change. And certain cryptography, in the medieval period, for example, they continued for 100 years. But then again, it had to be changed because of emerging technology. So today, as the speaker was talking about, modern cryptography is based on mathematical problems, particularly trapdoor problems. Now, it is vulnerable to certain facts. First is human intelligence, because it is not provable that it cannot be proven to be, secure against. There is no proof as such that it cannot be broken. Second is the new technology, which is the quantum technology, which is coming, which I'll talk about now. And third is it allows you to have certain backdoors. And now, if you're talking about particularly security of keys, particularly encryption keys, we say that cryptography is secure as long as the keys are secure. So now, if you look at the transportation or generation of keys, today the generation is mostly algorithm based, and the transportation it can be subjected to active and passive attacks. There is no guarantee. You cannot find out whether it has been copied or monitored. Now, in quantum, when we're talking about quantum, then we are talking about cryptanalysis as well as the securing cryptography. So when we're talking about cryptanalysis, we're talking about particularly those quantum algorithms. For example, Shor's quantum algorithm, which is a polynomial time quantum algorithm for integer factorization. Because in classical, it can be broken in super polynomial time. So that is one of the major threats. Now there will be some more questions, as in what is the exactly size of a quantum computer we are looking at to break these kind of algorithms, which we'll come to later. And the other part is secure quantum keys. Now, theoretically, it is proven to be secure. So when I say theoretically, I'm meaning it on paper, but when we are implementing it from paper to practice, then of course the security is subjected to the way it is being implemented. But in quantum mechanics, there is a way where we can generate secure symmetric keys at two distant locations. So that is called quantum key distribution. So this is a hardware solution. I think we have experts here who will talk about the software part of it as well. But particularly, why is quantum key distribution exciting? Because if you look at encryption key, then its characteristics is it has to be random. In quantum technology, there is a way to generate quantum certified random numbers, which are information theoretically secure. Again, I'm keeping in mind that it is all implementation. It has to be, it has to be a very good, near to perfect implementation. When I'm saying it has to be probable, or it has to be secure. And second is the keys has to be random, and it has to be any type of eavesdropping attack on transporting the keys or any kind of tampering with the keys, we should be able to detect it. So that provision is also there in quantum key distribution. So it is very interesting application of quantum information science. Again, quantum information science is nothing but marriage of quantum mechanics and classical information processing. So this kind of a technology, I think, will lead to a future-proof technology, cryptographic technology, because here the adversarial model which we look at for quantum secure communication is limited by physics. It is not limited by technology. So when we consider attacks, not only we are considering the information leakage attacks because of non-ideal components or transportation, but we are also looking at the power of quantum adversary and taking that into account when we derive the secure keys. So I think this is a time, and this is a very exciting time, and at C-DAC being the Center for Advanced Computing, we are attacking at both these technologies, particularly quantum computing. So very soon we are coming out with indigenous solution for a quantum computer based on multiple technologies. And we are developing quantum algorithms. We have Atos quantum computer also with us. We're looking at, developing these indigenous cryptanalysis based algorithms, quantum algorithms. And also we are actively looking at quantum secure communication, which has been done in collaborations with Indian academic institutes and industry partners. So we are moving in this direction.
Yeah, thanks, Dr. Banerjee, for this very interesting discussion on quantum computing and its possibilities. Now, a very interesting thing is you already mentioned in your talk is that as of today, we don't have such large-scale quantum computers which can break the classical techniques. However, we all of us believe, even in the standardization bodies like NIST in the USA, that such computers are going to come up. Maybe it will take a decade, maybe 5 years, we do not know, but they are going to come up. And as we already know, change management of cryptographic algorithms is very, very hard. So when MD5 and SHA-1 were broken, they are still found in many implementations in industry today. So NIST has already started going in development and standardization of algorithms which can resist even when quantum computers come. And we have with us Dr. Shweta Agarwal from IIT Madras, one of the leading lights of post-quantum cryptography from the country. And some of her work has actually made a mark at international stage. And we are very fortunate to have her with us to discuss about this post-quantum algorithms. And I would like to now request Dr. Agarwal to shed some light on what kind of mathematical hard problems are being used and what is the future for post-quantum cryptographic algorithms for us.
Thanks, Saumitra, for the introduction, and thanks also for the invitation. So, as Anindita already mentioned, so she talked about two aspects of quantum computers as they intersect with cryptography. The first is in designing cryptography, and the second is in breaking cryptography, right? So now, yes, even though we don't have large-scale quantum computers at the moment, the threat of them is real, and it's going to take a while for us to move to quantum safe technology. So therefore it is well understood that the effort for designing post quantum secure cryptography is very, very urgent as of now. Now here I would say that using quantum computers to build cryptography, this is something that is scientifically interesting and a bit futuristic, because yes, we want to also harness the power of quantum computers for constructive purposes. But even more important and urgent in a short term, in the short term, is to protect against the adversarial power of quantum computers, right? So post quantum cryptography is about having an asymmetry between the designer and the attacker, where the designer is assumed to be classical, which is where we are right now, and the attacker is assumed to be quantum. So the quantum attacker could sort of show up at any moment. I mean, maybe there's some country or some lab which develops the first quantum computer that is able to break classical cryptography, and we want to protect against that, but we don't have quantum computers to protect against that, right? So basically we're protecting against the all powerful adversary. So this is the area of post quantum cryptography in which I have a particular interest. And here there are a variety of mathematical problems. In fact, I wrote a short book chapter at a very introductory level about about this very subject. So for those who are interested, you can find it on my webpage. But primarily, post quantum cryptography is going to be uh, is currently dominated by problems such as lattice problems, isogenies, code-based problems, multivariate polynomial equations, and there are really several others as well. And where we are, I think, with post quantum is that uh, in the NIST competition, there is a standardization of basic or a call for standardization of basic cryptographic primitives such as digital signatures, public key encryption, um, basic cryptographic primitives, right? And here I think that we have made good progress. So we have we've had constructions in the theoretical regime for quite some time, and now these constructions have been sort of studied suitably, and the parameter ranges where they're going to be secure, these have been analyzed thoroughly, and implementations are there. So based on different mathematical conjectures, of course they are only conjectures, as Anindita also mentioned, we do have things that we conjecture to be quantum safe, so against a quantum attacker. And in the theoretical domain, we have even a lot more, like we have a lot more uh, material, so to speak, right? That feasibility results where we know that something can be done in theory, but in practice it is still taking, I mean, there's still a ways to go before it can become practical. So yeah, all in all, I think globally there is some good understanding now of basic cryptographic primitives in the post quantum regime. And advanced cryptographic primitives, there is a theoretical understanding, but we're still working on getting more practical candidates. So that's where we are, I think, with this.
Thank you very much, Dr. Shweta. And now I want to talk about, now that we just discussed about the foundational principles of security using purely math and using the quantum math, the quantum physics. How is it possible to keep us secure on the internet? But I want to come back to now one topic that Dr. Vireshwar mentioned in the initial points made, and that is that he also has a lot of interest in network security and network protocols. Now, some of these protocols, if you see, of course, at the underlying stage, they are using cryptography, but many of these systems are rule based. So you have a rule, for example, in firewalls, and we know that some of these rules can be conflicting. It's not very easy to even identify if any rule is conflicting with another rule, because there could be cyclic dependencies between them, and these problems are exponential time, or I mean, certainly not polynomial time to solve. And in this setting, do we have any way of using mathematics to automate this reasoning and find out if the rules of firewall are indeed the valid? So, Dr. Vireshwar, any comments by you on this?
Yes. So as has been highlighted by other speakers, that so we have some algorithms which are on the table. So we have some algorithms which have been proved on paper, and then we have some algorithms which have sufficiently robust implementations, even the existing ones. So now, when we want to verify whether they are actually secure or not, so then there are certain methods in which we could do it. We could look into the area of formal verification. We could look into the area of program verification in order to see if that is possible or not. So now, for the conventional crypto algorithms like RSA, Diffie-Hellman, and others, so we we definitely have. If we assume that the basic cryptography remains secure, then people have actually come up with tools which would be able to analyze a crypto protocol that you build using them, and using this idea of formal verification to show that yes, the protocol that you have built, the code that you have written, that is definitely secure. So there are some existing tools to do that. Now, as I said, that this is a 3-level process. So we have the crypto primitives. So let's assume that the crypto primitives are secure. Then we can say that protocols could be secure. So even some protocols like TLS 1.2 have been shown to be secure by doing this analysis. Then, but there is a third level where we are looking into the network security. So that is something which is very difficult to actually build any mathematics to prove that your network is completely secure. Now, I would like to also add here that when we are doing these kind of verification techniques, it takes significant amount of effort. So it is not very easy. So of course, developing a secure crypto is very, very difficult. I'm sure Shweta can tell us about that. And then, converting a crypto protocol and into a language in which the formal verification can be conducted, that itself is a very difficult task. So if you look into one of examples like TLS 1.2, it might have taken the researchers around a year or a year and a half to first bring it in that format where that tool could run its analysis to check whether TLS 1.2 is formally secure or not. So therefore, that is another angle, that it is currently, although there are some existing tools to verify if they are secure or not, but then the effort is still large. So there is still a lot of effort required in order to make this whole process so that fast, so that we could actually have quick feedback about the security of these scenarios.
Okay, thanks, Dr. Vireshwar. So I want to come back to Dr. Anindita. So is it possible to have some quantum algorithms for speeding up this verification protocols? And second thing I want to ask you is about, is there anything happening on standardization process of this quantum implementations? The reason I ask you is because when industry tries to implement things, they are not going to look at research papers where algorithms are described, for the reasons that they need to be interoperable with the other industry implementations. And this is the reason that Dr. Shweta already mentioned about NIST spending a lot of energy in last 2 years about post-quantum crypto algorithm. So not only the algorithms per se, but even their specific parameters are being discussed and being standardized. So do we have something like this in quantum world also?
So, so when we talk about standardization, or let me talk about quantum safe cryptography. So one aspect we cover it is using post-quantum cryptography, which Dr. Shweta was very nicely, she brought it out. Another aspect is quantum key distribution. And third would be, since there is no per se standardized protocol as of now, but there is a need to go for quantum safe transition. So many organizations are going for hybrid model also, where they have post-quantum cryptography, quantum key distribution, and classical. Because whatever we say, but still our stronghold is still in classical. We have been working on this for 70 years. Quantum is new. We have to understand. And as Dr. Shweta may agree that, quantum safe cryptography also we'll have to explore from many angles, look from the quantum adversary point of view. So, and then there are standardizations happening in quantum world. For example, European Telecommunication Standard Institute, Cloud Security Alliance, NIST, they are coming out with so particularly quantum, let me say, quantum entropies, specifying what are quantum entropies in case of quantum random number generator, defining the quantum random number architecture. So ITU has been very active in that. Then what are the different ways or different, so there are different modules. You can break the quantum key distribution into many modules, and there have been white papers on how to select the protocol sources, how to characterize the components used in this in the QKD. So yes, there is happening, and it will take maybe few years more, maybe less than a decade, to come out with a complete standardization. QKD network standardization is happening. Then there are the interface between the between the classical and the quantum. So in those areas, standardizations are happening. But for quantum per se, it needs a lot of research, and it is still evolving. So we need to be proactive. We need to understand. To bring those clarity, there are certain white papers which we can follow. And it also helps me to follow those papers, because then the transition to standardization becomes easier in future. So yeah, one can look into these papers and understand what kind of standardization is going to come in.
Yeah, but there is no standard body like NIST in this area, which is trying to standardize these algorithms implementations right now.
NIST is doing it very actively for post-quantum cryptography.
Yes, indeed.
And it is also implementing quantum key distribution or quantum communication, quantum internet. It has been active in these areas as well. But per se, quantum key distribution, HC is taking it. HC and ITU is taking it very actively.
Okay. Thank you very much for your comments. So I also want to bring the discussion to a slightly different area now. So maybe about 20, 30 years ago, when these papers were published first time, things like zero knowledge proof, they were considered just theoretical constructions. And the first time as a student, when I read this paper, it blew my mind. What a wonderful concept it is that we can prove something without telling the thing, and the other party is convinced. But today we see the era has come where these techniques are not remaining any theoretical. These problems, which are again based on some beautiful mathematics, are now being utilized in practical protocols like Zcash. The cryptocurrency uses this zero knowledge proof in a beautiful manner. So I want to come back to Dr. Shweta now and ask, maybe request her to comment about these kind of supposedly futuristic technologies just a decade or 2 decades ago, and how they are slowly coming into practice, and what is the mathematics behind this, and how do we see this space growing up in maybe in future industries?
Yeah, so Saumitra, the space of zero knowledge is also, I think it's the favorite space of every cryptographer, everyone who has studied cryptography. And it's also a great example of something that, is dismissed initially as a theoretician's mind game. And, later you find that, no, in fact, it is very useful even in practice. I want to point out that fully homomorphic encryption is another such example where, when it first came out, well, the very first construction in 2009 was, of course, very messy, based on non-standard assumptions, extremely impractical. And I was doing my PhD at the time, and I remember that, there was a lot of discussion that, even later on, after I moved back to India, I remember at IIT Delhi, we had some event, and people were saying that, oh, it's just a theoretician's something. It's not something that will ever be practical. But you can never really predict the advances of science. And now, in fact, both zero knowledge and FHE, especially zero knowledge, I guess, have been implemented in many important and interesting applications. So I think this is a great win just for theoretical cryptography, right? And yeah, as a theoretical cryptographer, I want to emphasize this point, because we are often critiqued for developing things that we like to think about, but you never know which thing is going to be very important in the coming years. So now, coming back excuse me, coming back to the question of zero knowledge. So zero knowledge, as you pointed out, is this idea that I can prove to you something without telling you what I know. right? And when I introduce the subject to my students, for instance, I always give the example of a Sudoku puzzle that, let's say that all of us are trying to solve this puzzle, and I claim that I have a solution. Now, the traditional notion of a proof is that I show you the solution and you verify. But in doing so, I also leak the solution and spoil your fun. So, is there a way for me to prove to you that I know the solution without leaking the solution? And indeed, actually using playing cards, there's a very cute way in which you can do it. So, it's a nice way to, get the flavor of zero knowledge. And ZK has been used a lot, especially recently in the context of blockchains. As you mentioned, you mentioned Zcash, for instance. So there, you can, in a cryptocurrency, for instance, you have this tension between privacy and verifiability, right? So, for instance, you would like your transactions to be private, but you want to make sure that these transactions are valid under whatever consensus rules the network has. So something like zero knowledge lets you do that, because it lets you encrypt the transactions and prove in zero knowledge that whatever has been encrypted is valid under whatever rules you specified. And zero knowledge can be based on multiple assumptions, both classical and sort of traditional classical and post quantum. And especially lately for succinct zero knowledge like snags and so on, doesn't matter if we don't expand that out, but basically, very efficient zero knowledge proofs, there has been a lot of progress that makes use only of simple symmetric key cryptographic primitives. So these are efficient as well as post quantum. And also in the lattice regime, there has been a lot of progress in developing zero knowledge for restricted algebraic statements. So basically, in terms of a feasibility result, we have zero knowledge for sort of general statements. But in terms of efficient zero knowledge, based on what mathematical assumption you want to make, we have constructions from different assumptions, some of which are also post quantum. So there has been a lot of progress in this space, going from feasible to practical. And it's already being implemented in several applications like cryptocurrencies and so on. There's also a very interesting application that was developed in the context of nuclear disarmament, that you want to prove that something is not a nuclear weapon, but without leaking sensitive information about how it is constructed and so on. So there are applications of this idea, in far reaching spaces. And it's something that we expect it to become more and more widespread, its use.
Yeah, thanks. You made a wonderful comment about us not being able to predict future, and which is why it's very hard to make a decision about what is practical, what is going to be practical in future. In fact, I saw a wonderful discussion about this somewhere, where some papers were being rejected. Even the classic paper on zero knowledge proof, as you mentioned, was rejected a couple of years, and today it stands the test of time. And in fact, if we look at many of the test of the time awards in our own domain of cryptography, we realize many of these papers never received best paper award. Okay, so but they stood the test of the time. So we are not very good at predicting future as technologists. We may be good scientists, but the way the world goes, it's very hard for us to decide.
I was actually not necessarily pointing to scientists here, but just humanity at large. As for paper rejections, I think that there are so many factors, it should not be taken very seriously. But indeed, indeed. Go on.
Even among the results which were considered exciting by the community, some became, not so exciting, and some which were not considered exciting became very exciting for the humanity overall. So this is something that very hard.
Although maybe because I serve on so many program committees, I do want to say from the program committee point of view that rejections don't always mean that the paper or the idea is not exciting,
Yeah,
right?
correct,
It could
correct.
just mean that maybe it is not presented so clearly, or
Yeah,
maybe, it is not very clear how it compares to
yeah,
other
indeed.
works and
Yeah,
so
indeed.
on. So I
Is
think rejections
Yeah,
should not be thought about
Goldreich
at all.
mentions in one of his books or essays that a rejection essentially means that that particular work was not suited for that particular conference or a particular session. So, so maybe that is the way to go about. So we had a very interesting and exciting discussion on various aspects of cryptography, security, automated reasoning, and so on. I think our time is up, as I see from the watch, the clock here. So thank you very much. It was wonderful discussing with you, and hope to have more such sessions organized by DSCI. I also want to thank the Ministry of Electronics and Information Technology for giving us this opportunity. Thanks all of you. Thanks, Dr. Vireshwar. Thanks, Dr. Shweta. Thanks, Dr. Anindita, for making this exciting conversation today. Thank you very much.
And thanks to you, Saumitra, for
Yeah.
organizing it so well.
Thank you.
Yeah. Thanks, Sumitra. Yeah.
Thanks.
Thanks,
Thanks,
Shweta.
Sumitra.
Thanks, Anindita.
Thanks. Bye-bye.
Bye.
Bye-bye.
Bye. Bye.
Bye.